break. We started but could not complete our lecture series. So, I see low attendance here. Do we have E22 and 23 both batches represented here, or it's just one batch? 22 batch in 22. 23 is also there. So, only very few from 22. Is that right? Many, can you please raise your hands? 22? Okay, there is. Right, anyways. So, we are going to start, and it might run until 12:30 or a little bit later. So, because it's a Friday, Muslim students feel free to get up and go to the mosque when you need. Any others also, you know, you can leave whenever you want. But I will be recording the lectures and uploading for the benefit of those who could not come due to various reasons, due to weather related issues. So, I plan to record these lectures in next couple of weeks, so that it can be kindly please be quiet, because we are recording it, and if you have any questions, please do ask, no problem with that. But we need to we need to cover a lot today, so hopefully we'll be able to start. Any questions before we start from the previous lectures? I have uploaded all the material. The lecture notes is also there. So, more than taking down lecture notes, pay attention to what we talk about and ask questions, try to understand. Well, the lecture note is already there, but it's okay if you want to take down. So, when you take down, sometimes it processes and then memory consolidates. So, it's okay. I'm going to, there are two attendance sheets, one for E22 and one for E23. I'm going to pass both. I'll pass one from this side and the other. Please make sure to pass both, okay, because one is for 22, the other is for 23. Leave the first column first after the bonus. There's keep one column open. Don't sign on that from the second one. So, that's the second date, okay. Right. So, shall we start then? Okay. So, last week we started the lecture series by basically reviewing circuit analysis methods. Right. If you can remember, the purpose of circuit analysis method that we talked about was to figure out the currents and voltages in a simple circuit. Right. In a circuit, we want to find out the currents and voltages in each branch and across device components. For that, we learned several methods. We said that the basic method was applying Kirchhoff's voltage law and Kirchhoff's current law to each mesh and each node. We can write several equations. We can obtain, if you have n unknowns, we can obtain n equations, and solving these n equations, we can obtain these currents and voltages. This is tedious because you have large number of unknowns and large number of equations. So, typically it needs a lot of working out. The second method we talked about was the circuit composition rule, where when we don't need all the currents and all the voltages, typically what we need is for one maybe output current and one output voltage. So, in such situations, we said we can combine parallel resistors and parallel series resistors and voltage sources and current sources in such a way that you can simplify large networks into a very simple circuits. So, that applying Kirchhoff's voltage law or current law, you can basically calculate the current or the voltage that you need, right. That also we looked at. The third one is basically the standard method that is used almost everywhere, especially in circuit simulation software, circuit analysis software, where you have a circuit, you identify one node as a reference node, and you are not going to calculate currents. You are only finding voltages of values with respect to that reference node, and those nodes for which we can directly get the voltage. Like for example, if you have between two nodes, if you have a voltage source, you know, you can with respect to one node, you can find the other node's voltage. So you mark them like that, so that we minimize the number of unknowns and write the node voltages of only those unknown nodes, right. That will be a handful probably in a small circuit. So that for that, each of those nodes where you don't know the voltage, you write Kirchhoff's current law to these nodes. We call this nodal analysis. We apply nodal analysis to each of these nodes and write down equations. Once you write down equations for these nodes, there will be 5 or 6 or whatever, however many, depending on the size of your network, you will have several equations, and it will be similar to the number of unknown voltages, because we are applying for each unknown voltage node, you apply the nodal equation. So, you will get one equation for each of these. And then once you have this, in terms of these unknown voltages V1, V2, V3, we get n number of equations. We can solve it using linear algebraic techniques. Typically what we do is we write it in matrix form, right. Ax equals to y kind of form in matrix form. So, x is basically the unknown and y basically is the, what you will get is y as the sources, right, voltage sources and current sources and things like that. And what you do not know, the matrix is x, and A is basically will be obtained, will characterize the network, right. And then by inverting the matrix A and multiplying by y, you easily obtain x values, right, unknowns. So, that is what we talked about, and there for these three techniques will work for any network, whether it is a linear circuit or not. Okay, whether linear or not, this works. But for special cases where the circuit is linear, right, when you have only resistors and voltage sources and current sources independent, linear circuits, in such situations, even dependent voltage sources and dependent current sources, as long as the circuit is linear, there are no nonlinear devices like diodes or transistors, things like that, then you can apply three other methods. One is superposition. Probably we haven't covered it in the class, but we don't have time to go through it today. In that case, what you do is you apply each of the source, independent current source or the independent voltage source at a time, and find the voltage that you want to find, assuming there is only one source, replacing the other sources with their internal resistances. If you have a voltage source, typically the internal resistance is 0. So, you short circuit such voltage sources. If you have a current source, typically the current sources have very large input impedances, output impedances. So, typically we represent them as open circuits, right, open circuit current sources, short circuit voltage sources, remaining only one voltage source or current source at a time. Find the current or voltage of interest for a given single voltage source or current source, and then go through each of these sources, add the values together later. Okay. So, that is the superposition. Probably you have you should have learnt it in the first year. I have also included 2 videos about how to do this on the Fields course web page. Hopefully, you have gone through it already. And also there are other 2 methods, the Norton's equivalent circuit method and the Thevenin's equivalent circuit method. We will be using this in our course, where any part of the linear circuit can be replaced between 2 points with a current source, voltage source and a series resistance in the case of Thevenin's equivalent circuit method, or a current source in parallel with a resistance in this case of Norton's equivalent circuits. So, you replace large circuit parts with just a source, right. Thevenin's or Norton's source. So with that, you simplify the circuit and then analyze the circuit, right? We will be doing this for BJT circuit, so we'll learn about it when we get there, right? So that's what we talked about so far, and hopefully, these are very simple techniques. None of these need too much, very advanced mathematics or anything. Very simple addition, multiplication, division kind of things, right? No integration, no differentiation, partial differential equation solving, nothing is there, right? So that is why in this course, your life is very simple, right? Why it is simple? But what we are going to talk about is, in reality, the life in nature, life is not simple. There are so many complex interrelationships between various elements, and things are nonlinear, and various complications are there. So what we are going to do today, the topic of today's lecture is abstraction, which is a technique that we use in engineering. That abstraction is what converts this complex natural world into something that is very simple, like working with addition, multiplication, and linear algebra kind of things, right? So that is basically what we are going to see today, right? Any questions before I start this section from previous lecture? Any questions? Okay. All right. So let's then get started on today's lecture, which is called abstraction. As I said, lecture note is already available online, so you, if necessary, you can take a printout and come or whatever, that is fine. So what is abstraction? Abstraction is basically, it's a process of hiding complex physical details, right? There are systems with a lot of details, right? So the abstraction basically hides complex physical details to focus on simplified high level model. Now there's a lot of things there, right? So if you take, for example, a radio, or maybe let's take an op-amp, operational amplifier, right? You know operational amplifiers, you have done it in the advanced level. We represent it like a triangle with plus and minus and output. So it's a very simple abstraction. We call it an abstraction. What is inside this thing? We don't know. You don't have to know. What is inside that is very, very complex, right? There are sometimes hundreds of BJTs and FETs, transistors, inside a single op-amp, but you don't see it. All you see is a triangle, and that is characterized by a very high gain, very high input impedance, and a very low output impedance. That's all you have to know about it, right? So that's the abstraction. We don't see what is inside. It's a black box, right? So it creates a black box where we can we care about only the relationships between input and output. Okay, we don't care how it is done, what is done. In the black box, there may be complex things, but if you give 1 volts, output may be something that you want, right? So 5 times 1, something like that. So that's all we care about. So this is, we don't care about the internal implementation, but we care about how it behaves. So and what you need to remember is that these things work as they, as we model it, simplify it, only under certain conditions, not generally, not universally, right? So that is where, that is what we are going to do today. Without this abstraction, without the abstraction, it would have been extremely difficult to do any of the things, to achieve to design any of the things that we use today, cell phones, space shuttles, video games, these complex things, the radios, things like, would be very difficult to do without the ability to abstract. Because if you had to deal with all the fine details throughout, you wouldn't have been able to do this, right? Can't do it because too complex then. So that is what we are going to do. How are we going to go over this gory details of this nature, right? The nature has a lot of things, right? If you take a light bulb, simple light bulb, when you switch the switch on, it lights up. What we care about changes on the situation. For an electrical engineer, what we may be interested about may be the voltage across it and the current going through the filament. But for someone else, maybe the light intensity may be what is interesting, right? For someone else, maybe the temperature is what is important. If you are interested about hatching eggs, like incubators. So a simple light bulb itself is a complex thing. But if you want to represent, if as an electrical engineer, if you want to look at it as a circuit, you only care about the voltage and current, isn't it? So though a bulb or a simple light bulb with a battery is a complex system in the nature, battery itself is a complex thing. You have a lot of chemical reactions going on, and how these are connected to the wires, that's pretty complex. But we don't care about it. We represent it as a battery with a voltage, a fixed voltage. We don't care what the current is. No matter what the current is, you have 1.5 volts. That's what we represent the battery with, right? And that basically we achieve that using abstraction. But actually, is that all that we have? No. Battery, if you heat it up, will it work? If you cool it down to a certain degree, will it work? It doesn't get captured, right? We care about only. So we say, okay, this battery works from maybe minus 20 degrees to 40 degrees Celsius. Okay, so we limit ourselves there and use it likewise. Okay, so this abstraction comes initially. So this is basically simplification, so that we can use them in some purpose. Otherwise, we won't be able to use these physical principles, right? So to start with, what we have is the nature. So nature is what you have. Nature is very complex, interrelated, complex, right? But then what we do is we simplify it for the purpose of our analysis. Like, say for example, laws of physics. So you simplify it, the laws of physics, right? Okay, what are laws of physics, right? For example, now this is the hardest, this is the class where I use the most gory details of in this class, okay, in terms of mathematics, right? For example, Maxwell's equations, right? Just to give a glimpse of what Maxwell's equations are. You might not have seen Maxwell's equations so far, right? So, but you have done it actually. You know Gauss's law, right? You know Gauss law, you know Faraday's law, you know Ampere's law, all these you know, right? You know, when you send a current through a wire, it produces a magnetic field. That's Ampere's law. If you have a changing magnetic field, if you have a wire loop, a voltage is induced between in the loop. These things you know, right? So that we write in terms of, this is Gauss's law. This is Gauss's law. Have you used this notation for the Gauss's law? No, right? This is Gauss's law. We can use it like this, or also if you have a closed surface, if you integrate the electric field coming out of it, that should be equal to the charge inside this, right? So that's basically the Gauss's law. Right, so that's Gauss law. And then for magnetism, you have, you can't have single poles, so therefore this should be 0, right? And you have del cross B is equal to minus double B over double T. What is this? Faraday's law, right? And likewise, you have the Ampere's law. This is when you send the current. So this is E, this is P. Sorry, this is the Faraday's law. This is Ampere's law. Mu naught epsilon naught. You may not have seen this part, but double T plus mu naught J. So this is the current and magnetic flux, right? So it's pretty hard to work with this, right? If I had to use this every time I have to analyze an electric circuit, not many will be doing engineering, right? It's very difficult, right? So we don't want to do this. That is why we want abstraction. So the first thing that we do is we abstract it out to do what is called circuit and element abstraction, right? And electronics. So this is important for physics, right? If I ask you what is 100.25, so 101.25 times 198.92. Can someone tell me quickly? Difficult, right? It's difficult, right? Isn't it? But I can say this value is very close to, this is like 100 times 200. If I give it like that, this is very easy, isn't it? The value here is 20,140.65. What's the difference between these two? Not much. Less than what? 1% or 2%, maybe. Definitely less than 5%, right? So whenever you want this particular value, if I use this value, is it going to make much of a difference? It's just 1% or so 1% or 2%, very small value, right? Not much. It's almost the same value. Why? In order to find this, you have to do a lot of work. In order to find this, very simple, isn't it? So this is kind of what we are going to do here. We don't really care what this is, right? We only care about the big picture. So this is where we kind of ignore some of these things and we restrict ourselves to certain that we call discipline. We say, okay, I don't care if this is more than that or less than that, I don't care. I only work with this small region and I only always work with these values. And any time that it goes beyond that, let me handle separately. Okay? So most of the time I will be working with this. Okay? That's what we are going to do. Okay? So this circuits and elements, what I am going to do is I am going to replace these equations and everything that are applicable, say for example light bulb, with some simple things. I am going to represent the filament of a light bulb rather than worrying about the flux intensity it produces, rather than the temperature, the size, the color, all these things in the nature, it's all there. I don't care. I only care about its current and voltage relationship. So if that is the case, I can represent the light bulb as just a simple discrete resistor. And this represented by just one simple number, R, right? And I only care about the relationship between the voltage and current, isn't it? As long as I only care about voltage and current, this one number is good enough for me, right? Likewise, a switch, a voltage source. These things, I say I don't care what the current is, the voltage is E. This I have either 0 or 1, on or off, right? So voltage will be either 0 across this or the voltage that is applied across it, right? So very simple. So this is basically, these are called ideal components. So you can use what are called the simple circuit laws like KCL instead of this, KVL instead of from this you can obtain another equation which is called the continuity equation, that, right. So KVL and Ohm's law. Simple, isn't it? This is very simple. This is what we are going to do. So from this to KVL, KCL, from partial differential equations and integration and differentiation and systems of differential equations to arithmetic, linear algebra. Very simple. Okay, what enables us is this abstraction. Okay. So, and then we can simplify it. We can simplify it further from this circuit level to transistor level, right? So this is device level, device or transistor abstraction. Abstraction. So you have a BJT. Let me use a color. You have a BJT. So this is difficult, right? So I abstract it out. Let's say for a small signal, we will get to that, but later we will see that we are going to represent it as a model like this, right? Base collector emitter, base collector emitter. Simple, right? What you have now, this one is difficult, right? It behaves kind of funny. This we know how to deal with, isn't it? This is just a linear circuit. Nothing nonlinear is there. Okay? So for certain ranges of voltages and currents and inputs and outputs, we can use this. MOSFET. I can say this is a switch between the drain and source controlled by the gate. This is the gate, drain, source. That's much easier to work with, isn't it? Right? That's abstraction. That's abstraction, right? So this is the transistor abstraction, right? So now once you have the transistor, you can have two parts: analog signal, analog electronics, digital electronics. Let's first look at analog electronics, right? So this divides into two: analog path and digital level. So digital abstraction and analog abstraction. Analog abstraction and digital. Let's have a look at the analog abstraction first. Right? So you have transistors. Now what we do is, using transistors, we develop amplifiers. You can use these transistors to design analog amplifiers, isn't it? So we will be doing it in this class, right? So that is basically amplifier abstraction. This is analog path, not abstraction. So let's say analog path, analog abstraction. So you use these models to develop amplifiers. Let's say, for example, so this is basically the amplifier circuit. this is V in, V out. Rather than going into all these gory details, I represent this as A. So, this is the amplifier with input impedance R in, output impedance R out, and the voltage gain of A. I do not have to know about these resistors, the characteristics of the transistor, nothing, right. So, I abstract it out to just a simple symbol with input, output, and just 3 parameters. Yeah, isn't it easy? So, if I give this instead of this, isn't it not easy to work with this than that? When you have this to find currents and voltages, this is easy, right? If I know the voltage here is something, let us say V1, V in, I know V out is A times V out, right? Simple to find. Yeah. So, that is basically the amplifier abstraction. Okay. Similarly, there are other things like amplifiers. This is an amplifier, right? There are what are called analog amplifiers components like current mirrors, differential pairs, voltage references. These are some of the analog amplifier blocks. Okay, so then you can use each of these small blocks to develop bigger systems. Okay, so like we use just the gain, input impedance, downstream. So we know how this behaves, and when we put this block in, we don't care what is inside. We know how to work with it. Likewise, these things are also like that. So you put these things to develop much bigger systems. The next abstraction level is an op amp. Op amp abstraction, where you combine a lot of these things. As I mentioned, there are hundreds of individual components inside these op amps. We do not see it. And then what we do is we represent it simply as a simple device, op amp, right? And input impedance is infinity. Output impedance is 0 and gain is infinity. Now what? Now this is even easier to work with, right? You have worked with this in your advanced level, right? Op amp circuits. So this is much easier. So you work with op amp circuits, right? So we develop analog systems using these op amp kind of things. So what are some of the examples? You can use filters. Okay. Filters, oscillators, power supplies, then modulators and demodulators, things like that, right? Comparators, instrumentation amplifiers. A lot of applications we can build using these op amps. You combine them together and develop bigger systems. Now, if I at the point of developing this modulator or the oscillator or filter, if I have to use Maxwell's equations, it will be very difficult, right? It would be very difficult to deal with it, right? Because there are so many components inside each of these circuits, right? So that's basically, so for example, I can use filter, right? Very simple filter, right? And I know it will have a certain characteristic with frequency, gain, has a certain characteristic. Okay. So, the analog systems. And then we develop what are called, so this is analog system blocks, analog system blocks. And using these we develop real analog systems. Like what? Radios. Analog radios have been using for ages, right? Radio. Radar systems, analog radar, right? And then we can have toasters, we can have analog controllers, voltage regulators, so these are all some analog systems. There are many, right? Anything that only use analog, you can use using these things, right? You are doing the sensor systems. You have been doing this, right? Yeah, you have been using. So easy to do this. When you pick the EE2040 op-amp and build circuits using this, you don't care what is inside it. You don't care how the resistors are there, what are the values of resistors inside this op-amp. You don't really care. You don't have to, right? That's what abstraction does. Okay. And then this is the analog part, and then still there for the mixed signal, analog digital combined systems are there. So the digital path, in the digital path also you have several things. We take the MOSFET, for example, as a switch. If you have a switch, you can represent it as on off, discrete, right? Digital systems, right? So digital abstraction. So you have MOSFET, as a switch, on, off, in other words digital. Okay, so how can we do this? So this is basically, I have a switch, gate controls the switch, and this can be represented as with VGS, that is the voltage between this and that. VDS is the voltage across this, as something like that. This is 0, this is 1, right? So this is VGS, this is VDS. That's a simple switch. Now you can use these switches to develop logic gates. Logic gates, right? So for example, I can do this. This is the input, this is the output. When input is high, when VGS is large, output is, sorry, this is the other way around. When this is small, this has to be, so this should be like that, right? So when VG is large, output is 0. Okay, sorry, this should be the other way around, right? So if I apply a large voltage, this becomes short circuit. No, what I had was correct. This is correct, right? So when VGS is large, this is short circuited, so output is 0. For if you input 1 here, this will be 0, output will be 0, right? So this is nothing but a NOT gate. So instead of having this circuit, I put this. Isn't it easy? Yeah, it's easy, right? So these are logic gates, and then I can combine logic gates. These are called combinational logic. right. So, for example, I can have something like that. I can write down x is equal to a times b naught plus c, right. Isn't this easy? So, if I want to design something to achieve a certain logic function, I can do that. It's a logic function. It only depends on the current inputs. As soon as I define the inputs, it decides what the output is. What's the next one? I want memory, right. So, memory abstraction. So, you get this using sequential circuits. So, you have, in addition to this functional blocks here, where you have inputs, you also have a clock pulse. You have a clock pulse as the input. Depending on the clock pulse, you have a different output based on memory, right. SR flip flops, right. So, these are flip flops based on flip flops, flip flop circuits, memory, right, things like that. So, once you have these, you can build what are called finite state machines. Have you heard this term before, finite state machines? Yeah. So, this is another, let us say, we'll go to this finite state machines. So, these are called finite state machine abstraction. Okay. So, you might have seen kind of systems where you have multiple states, and depending on the input you can go from one to the other. So, if it while it is in state 1, if you receive digital input 1, you go to this, or maybe there are 2 inputs, I do not know, and then from when it is there, if you receive something, you go there. What happens here? Likewise things, right. You have seen this, right. Have seen things like that. These are called finite state machines, right. So, you can build finite state machines when you have memory. And then when you have finite state machines, you can build microprocessor based systems, microprocessors. Microprocessors, abstraction. What are some microprocessors? Like you have this called instruction set architecture, ISA, instruction set architecture. Things like Intel, you have x86 architecture, right? x86 architecture. You have AMD architecture, and you had Z80. Initially you have architecture, and these are some of the architectures that you have. Hardware, these are hardware architectures. Registers, you have registers, you control them using some instructions, using instruction set architectures. So, right. So, these are called this. In order to do programming for this, we use assembly language. Assembly language. Assembly language architecture. So, you have, for Intel, you have a certain set of instructions, assembly language, right. Sometimes you might have done it, maybe in the future you will be doing it. You use this language rather than controlling the flip flops and things like that. What we do is we basically give instructions, fetch this from that register. Okay, likewise. So, these are assembly languages. There are languages to do that. On top of it, you have higher level languages like C, C++, Java, Python, that kind of thing. So these are programming languages, abstraction, programming languages. Programming languages like C++, Python, Java, things like that. So that you can use these to develop software systems. We have analog systems. Likewise, we can make software systems, right? So the next level is, I don't know, I don't want to, I want to combine these. That is why I keep coming this way is that. So let me rub this off for the time being and come here, okay? So this is connected. And this will get software systems. Software systems like what? Microsoft Office, or maybe Linux, or else Windows, Microsoft Windows, right? These are software systems. Windows, Linux, MATLAB, MS Word, all sorts of, there are billions of software systems, right, that run on digital systems, okay? And then what do? You combine these two together. You have a hardware system which can be controlled using a software. These are called mixed signal systems, mixed signal systems. Okay, so these are mixed signal systems. These are the ultimate applications. These are the applications. Space shuttles, video games, computers, hand phones, any system that has a hardware part as well as a software part, most of the systems that we have, right? So, mobile phones, computers, space shuttles, the list goes on. Now, what made us possible to develop these systems is abstraction. If we had to work with Maxwell's equations, will you be able to make these things? If you just had to, there are two signature sheets, okay? Two signature sheets, one for E22 and another for 23. Hopefully, you have sent it through the whole list. Anyone from this is for the 22. Anyone who has not signed? 22? So, signed. 23 probably has signed also there. Right, anyways, good. So, that is basically the abstraction, right. So you understand the big picture now? Why we need abstraction? This is why we need abstraction. Otherwise, we won't be able to do anything, right. So, now that we know what the power of abstraction is, let us now kindly, slowly get to this. We will try to abstract away from these gory Maxwell equations into nice Kirchhoff's voltage law, current law, kind of things. Okay. So, this is called, this abstraction, the first layer is called lumped matter discipline. This is called lumped matter discipline. This is called the lumped matter discipline. It allows us to simplify from physics of electromagnetic fields theory. So, let me write it down. To simplify from physics of electromagnetic fields. So, that is basically Maxwell's equations. to circuit theory. That is KVL, KCL, Ohm's law, that kind of stuff. We strictly adhere to a set of engineering rules known as lumped matter discipline. We follow a set of rules. In other words, we are restricting ourselves. We are not going to look at everything that is possible. We are only working in a restricted region. We are limiting our playing field here. It is a set of self-imposed. We have these limitations on ourselves. Okay? We limit ourselves. We discipline ourselves. Self-imposed restrictions we call discipline. That allows us to use what is called lumped circuit abstraction. Lumped circuit abstraction, LCA. Okay. So, lumped circuit abstraction is what enabled us to represent that filament with just one letter R, with one property R. We don't care about its temperature, we don't care about its color, we don't care about how long it is, the shape of it or anything. We just care about the relationship between voltage and current. That's lumped circuit abstraction, right? But this is you cannot use it. I said we are limiting ourselves. So, in order to use this, we have to define what are my limitations. We have to define when I can do it, when I cannot, right? So, there are three fundamental constraints. There are three fundamental constraints. Now, I will explain what one of these constraints in a bit detail soon, but let me write them down first. The first limitation, so these are limitations of lumped circuit abstraction. There are three. The first one is the rate of change of flux linked with any portion of the circuit must be 0 at all time. What does that mean? The rate of change of magnetic flux linked with any portion of the circuit must be 0 for all time. So, don't we have any circuits with where you have flux linkage? Right? You know, the first one seems to be very kind of, let's say the rate of change of magnetic flux linkage with any portion of the circuit must be 0. In other words, d phi over dt is equal to 0 outside the elements. Right. If I want to define my light bulb, flux linkage here cannot change. It has to be 0. The rate of change has to be 0. Okay. Within this, there may be changes. Inside the one, so we define the boundary in such a way that if there are any changes, that's within that boundary, but not outside. Okay? That's what this says. We'll look at why this is so. Why we need to adhere to this discipline, we'll have a look. Okay? Number 2 is the rate of change of charge. At any node in the circuit must be 0. 0 for all time. In other words, dq over dt has to be 0. If not, we cannot apply the Kirchhoff's current law. If, say, for example, there's a node, I send current, some charge is building up, so not all the current is going out. So it will violate the Kirchhoff's current law, isn't it? So therefore, you cannot have anything like that. You can have what are called supernodes. There may be sometimes, like for example, capacity. Inside the capacity, if you look what? There can be charge buildup. But you define the capacity in such a way that this whole thing is inside. The charge buildup is here. So the charge will go there, it will build up here, and some other charge will go like that. So if you take the whole thing, there will be no charge buildup. Okay? So you define the boundaries in such a way that this is not violated. Okay? So if you define your node somewhere here or something, you can't do it, right? Okay, so that's the thing. The third one is, now when something happens, light is basically, the electromagnetic waves are moving at certain speed, right? And if you try to measure things faster than that, then a wave front may not have received to a certain location. A current is flowing and sometimes it may not have. So therefore, the time scale, so this is, as long as we are working with low frequency signals, not very high frequency, very close to speed of light or something. Okay? Actually, there is a relationship between the lambda, the wavelength of the wave that we are working with. Like, for example, if we are working with 1 kilohertz waves, the lambda would be, so you can find the wavelength, right, in a certain medium. So for that, the size of the component has to be much bigger than that. Otherwise, you can't do it, right? So you will see these things. The time scale. Should be, time scale should be much larger than the propagation delay. Than the propagation delay. Of the signals, of the signal. So, the signal time scale must be much larger than the propagation delay of electromagnetic waves that propagate through the circuit, right. So, otherwise obviously a certain you may not be able to look at the Kirchhoff's voltage law or current law in that sense, right. So, now let us look at this. Rather than looking at all three, I will look at this. The uploaded lecture by the MIT professor basically talks about this, and also you can imagine this also how this happens, right. So, we will look at just one of these. Warning, this is where we use the most gory physics details in this whole class today, and that is it. And even that is just to convince you that we have to have certain these limitations in order to follow these abstractions. Okay. So, let us take that example that we took earlier. We want to find the voltage across a light bulb filament, right. So, voltage across an element, the element happens to be the light bulb. So, what we have is a battery connected to a light bulb like that. What we are interested about, the voltage and current. That is what we are interested about. Now, how can we use, if we did not use Kirchhoff's voltage law, current laws, you can't use it in general because these are complex things, right, unless we make them simple. So, how to use Maxwell's equations to find this relationship, right. The current through the filament when the voltage is applied. So, since this is not lump matter discipline, we have to look at it in its full glory. Let us say this is our filament, right. It has a thickness, it has a cross sectional area, right. So, and the current going through this and current coming out that, right. So, let us call this port X and this Y. Okay. Now, in order to find this, what we have is when we apply a voltage, there will be an electric field developed inside this filament, right. So, electric field is developed. That is the electric field, right, correct. Yeah. So, this is the electric field, and let me mark starting from here, this is the length L. So, this is the parameter L, right. So, in order to find the voltage across this Vxy can be written as using this basically voltage between the terminals, right, xy is equal to the integration, the negative integration of from x to y. So, from here to here is positive. So, therefore, if you are going this way to that way, that is why the negative sign E dl. So, if you integrate all these small pieces, if you add them, it becomes your voltage, correct? If you add them, so you add this plus this plus this plus this plus this plus, so you have the total voltage. That's the correct method to do it. From Maxwell's equations, so let's look at how to do that. The relevant thing that we have to use is this. dl is equal to, this is the Maxwell's equations. What is this law? Yeah, right. So, from flux to this, right, Faraday's law. So, you have not Faraday's, so this yeah, so this is the Faraday's law, yeah, Faraday's law. So, what you have here is something like this. This is the voltage, this is the flux linkage, right. So, if I draw this in general, what we will have is some loop. This is the Maxwell's equations, right, Maxwell equation around this, and if you have an electric field E dot dl, and so that's the contribution from this small length dl. You have to add them together. That's the adding, right, integration. And what is this? This is the flux linkage. This is d phi over dt. The magnetic flux linkage is this. So, if there is a time varying magnetic flux, will this be equal to 0? It will not. So, if you start from one point, add all the magnetic electric fields and come here, if there is a magnetic field varying inside this loop, there will be a finite value. It will not be 0, that is the induced EMF. So, Kirchhoff's voltage law does not do this, agree with this, correct? In order for the Kirchhoff's voltage law to be true, if you add all these voltages across this has to be 0, isn't it? That's what Kirchhoff's voltage law, if you go through a loop, if you add all the voltage drops, it has to be 0, isn't it? Then what should happen in order for the Kirchhoff's voltage law to be true? This has to be equal to 0, right? What does that mean? The flux linkage, the rate of change of flux with any part of the circuit has to be 0. Otherwise, it won't hold. See, that's this. The rate of change of magnetic flux linkage with any portion of the circuit must be 0. Otherwise, let's say only this part has a, okay, so there's a circuit like, okay, this is the whole circuit. Through this you have flux linkage, through here not. Okay, this part there is no flux linkage, so from here to here, that, so if you go through like that and like that, Kirchhoff's voltage law applies, correct. But this portion has this thing. So therefore, if you go through this, it doesn't, correct. So that is why for no portion there should be flux linkage. Understood this? Yeah. So that is the limitation. Likewise, you can also show the rate of change of flux. So rate of change of charge going into a node has to be 0. Otherwise, obviously, Kirchhoff's current law will not hold, right? And the third one. So therefore, if you take two closed loops, right, this is x, y, I take two paths. One path is from here to here, maybe from this. So this is path 1. Another path I take path 2. This is path 1 and path 2 from x to y. So, I am going to find the voltage using path 1 and path 2. Say for example, here the voltage between this in path 1 and path 2, right? Yeah. So, if I do that, the voltage from x to y is x to y path 1 E dl plus, so from here to here plus here to here, y to x E dl, this is path 2, has to be 0. So, this is x to y, this is y to x. So x to y plus y to x. So, this plus this has to be 0, right. So, this voltage plus this voltage has to be 0 if you add, or x to y path 1 EDL is equal to, if you take it to the other side, y to x EDL 0. If I change the direction, you can change the sign, x to y EDL equals 0. So, here from y to x, here x to y. So, the direction is changed. So, what this says is, it does not matter what the path is, they have to be the same. That only applies if this is 0, otherwise it will not. Okay. So, therefore, the voltage between x and y is independent of the path if d phi of dt is 0. So, let me write it here. The voltage between x and y is independent if independent of the path if d phi over dt is equal to 0, otherwise it is not true. So, that means Kirchhoff's voltage law is true only if d phi over dt is 0, right. So, if this is the case, we can write the KVL as sum of region along a loop. So, you have this part 1, part 2, part 3, part 4. So, each of these you can add, and about a loop, if you have a loop, this has to be 0. This is Kirchhoff's voltage law. This is KVL. Okay. So, likewise, we can also prove using Maxwell's equations. We can also show that in order for KCL to hold, daba Q over daba T has to be 0 as well at any node, right. So, I am not going to do that. You can, if you want, you can have a look at it online. Okay. So, that is that. I will just take 10 more minutes just to finish it, because we do not have time to complete this next week, right. With these three, I am not going to write things, I am just reading this. With the three constraints that we have here, if we have these, please, I am going to take 10 more minutes, please. With these three elements, with these three constraints, the behavior of the elements can be completely captured by the voltage current relationship, VI characteristics, for the lumped element, in this case the resistor R. Likewise, I might be able to look at a voltage source, a current source, a switch, or any other element, right. So, I can then only have to know what is the relationship between the voltage and current. So, for the resistor, I know the voltage current relationship, something like this, That's all I need, right? For a switch, I know something like that, right? So on off, like for example, the MOSFET switch, right? So likewise. So instead of differential equations in Maxwell's equations, we get to use simple algebraic additions and subtractions in KVL, KCL, right? That is called this is what is called lumped circuit abstraction. This is basically the lumped circuit abstraction. So instead of differentiation, we use differentiation and integration, we use addition and subtraction, right? So that's much easier, right? So we can create lumped circuit elements, can create lumped circuit elements. So in other words, completely characterized by terminal VI characteristics. In other words, we don't know what this black box is. It's some element. It can be a resistor, it can be a battery, it can be a voltage source, current source, anything, even some circuit, right? So what we care about is that this voltage and this current, right? This is a lumped element. And this is characterized by the relationship between this V and I. The V and I can be some complicated thing. We don't know what it is, right? It can be some strange thing. Like for example, it can be something like this for a diode. It's like this, right? Or it can be something like this for a Zener diode. Yeah. So funny things can be there. We don't really care what it is as long as you can characterize it like this. We say we only care about this and we know this. We characterize it somehow. Maybe a function of V equals a function of I, some nonlinear function, doesn't matter, right? So we have that. So in lumped circuit abstraction, okay, so you have instead of a battery I put this, instead of the bulb I put this. So what I always use this is the voltage between battery VE. This is the voltage between the resistor VR. The current going into this is IE. Current going into this is IR. This VR is equal to E. That value is equal to that. That's the voltage characteristic of a battery. So battery characteristic, voltage is always constant, equal to E. It doesn't matter what the direction of the current or the size of the current is, right? So it's like that. So this is the lump matter representation of the battery, and this the resistor. Okay. So we'll say ignore how current flows inside the filament. And so also one more thing, the power, when you use the LCA lump circuit abstraction, and when you put it like this, the power is always V times I. Power dissipation is always like that, right? So filament. We don't care whether how the current density, maybe the current density is very high here, no currents go there. Don't care. This is actually the case with what happens. The current density in the outside is high, no current inside. Okay, we don't care, right? Ignore temperature, shape, ignore temperature, shape, color, or any other orientation, size, doesn't matter. Only interested about VI characteristics. Can use simple laws like Ohm's law. Equals IR. R represents the only property that we are interested about. Interest. And R is a lump circuit abstraction of the bulb. Okay. So instead of bulb, now I have a R. Okay. So that's basically what you have. I'll just take another 3 minutes or so to write down the power of lump circuit abstraction. Power of abstraction. Power of abstraction. 1, manages complexity. What does that mean? When you define a black box, any system, for example, op-amp, we don't care what is inside, we just specify its terminal characteristics in terms of performance without giving the details of the circuit, what is inside or anything. Right? We just, system architect can specify an output op-amp's performance without designing its transistors, just as a programmer code an application without knowing the processor's logic gates. We don't have to know the logic gates, how they are, in order to write a C code or a Java code, right? So likewise. Number 2, enables specialization and reuse. Right? So if you go and check, if you want for an application, if you want a transistor, you have to know what kind of a transistor you need. BJT transistor, FET or whatever it is. Okay, it's BJT transistor. So when you want to take a BJT transistor, you have to know what kind of an application it will be used. You need high power application, low power application, high precision application, fast application, slow application. There are many different things. For different applications, there are different specialized elements. So you can't, for example, if you need for a fast application, you can't use high power transistor. High power transistors take time to recover the charge, so it will be slow. So if something is switching very fast, that won't work. If you, it is a BJT, but it won't work with a high power. If it's a high power transistor, it will not work for a high speed application likewise. But when you design, you don't care about it. The circuit you can use just using the transistor symbol. But when you pick the transistor, you need to know for what we are using, what are the requirements for that particular applications. Right? So specialization is important. And you can reuse them. Number 3, facilitates analysis and design. So what does that mean? So because each layer provides a simplified model of the abstraction and its own set of rules, it gives you a set of tools. Like for example, at the first layer of abstraction, instead of Maxwell equations, you had Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law. Right? Those are the tools. Once you have the discretization, you have the Boolean logic, right? So you don't have to say, how at what voltage a certain gate switches on or off. You can say A plus B equals to C. That is A or B, A sent through the O function, you get C, something like that, right? So those are the rules. And you can use, for example, SPICE for simulation. You can have a computer simulation because they know exactly how each of these behave under these constraint conditions, right? So this makes it possible to design layer upon layer, and once you have these high level blocks, like say for example amplifier blocks, power supply blocks, modulator blocks, and likewise, you can put them together like building blocks to build larger, bigger systems to achieve a much bigger task. Build a digital television using, you have to have a receiver, you have to have a demodulator, you have to have an amplifier, you have to have, likewise you can just concentrate on those things, right? And then when you want to implement this, demodulator. So what are the input specifications, what are the output specifications? You go to the Texas Instruments site or DigiKey or Mouser website and check for these specifications only. You don't care about how many transistors are there, what are the resistors used, you don't care about it. So you apply them and then decide the system level design, right? That enables you to design space shuttles and all these fancy things, the mobile phones, and all these things is because of this abstraction, right? So this is where I'm going to stop for today. If you have questions, please do ask. And also I highly encourage you to go through the lecture material that I have uploaded. I have specifically mentioned what specific chapters or sections of the textbook you need to read. I highly appreciate if you can do that. If you want to really understand this course subject, please do that. And also highly appreciate, still not done, the lecture notes by Professor Anant Agrawal. Please watch them if possible. Way better than my teaching. So please do. And I plan to have a small demonstration before you start the practicals to show some of the VI characteristics of. He shows this in his lecture, first lecture. So we'll try to have kind of a demonstration so that you also get the feel of it, right? In one of the maybe next week, maybe the week after, probably not the week of 24, then probably you don't have that much time. So hopefully week after that, we'll try to have demonstrations and do this, right? Okay, the next time when I send this attendance sheet, please write your first name in the first column. There's a space for first name. Please write your first name, because as I said, I want to get to know you by first name. When you write emails to me, don't write ABC Pereira, right? You write Amal Pereira or whatever that the first name. I like to be personal, right? So therefore, rather than writing your surname, write your first name and surname. Okay, that's what I would like to do. And any questions? All right, so we'll stop the course for this. Right? Thank you.